So our next speaker is Martin Losekamm, who will be presenting on a compact cosmic ray neutron spectrometer for lunar exploration missions. And we can see you, and we can see your slides. Looks good.
All right. Yeah, thank you, Ariel. And thanks for the opportunity to present our work here at this symposium, which is really great. So I'm going to present the development that we're doing currently on a cosmic ray and neutron spectrometer in general for lunar exploration missions. Just very quickly, because many of you and many excellent speakers before me have been touching on this this issue of water on the moon. So we do know that there is water on the moon. That is generally accepted by now. We have signatures of water and hydrogen that were detected by multiple missions. And in particular, because we're interested in neutron spectroscopy, we are obviously looking at Lunar Prospector and at LRO here. We know that water is supposedly stable in PSRs near the poles, and that we may have some transitional presence in other areas. What we're lacking really, and this has been mentioned before multiple times, is that we have no real in situ data yet. So this is what we and other groups obviously too are working on. Neutron spectroscopy is a really powerful tool to look for water because neutrons that are created in interactions of high energy cosmic rays with the regolith do interact with the regolith and everything that is in it. So the presence of hydrogen, could be water, OH, or any other hydrogen containing material, affects the neutron energy spectrum through moderation, and basically that leads to an overall very strong effect on epithermal neutrons with respect to fast and thermal neutrons. So the relative decrease in the epithermal neutron flux is a very strong indicator for the presence of hydrogen and water. And I'm just showing those two maps down here from the famous publications of Lunar Prospector and LRO. We can really see the decrease in epithermal neutron flux at the polar regions. So we're conducting this development as part of the so-called Lithiumyx project, which is a project to develop both a rover and instrumentation for the investigation of lunar volatiles. So that is a Horizon 2020 funded technology development project at this point, with the goal to do technology maturation up to TRL 4, 5, or 6, depending on the instrument and rover. It is a multinational consortium that's led by Space Application Services in Belgium. So basically the baseline assumption here is that we develop a rover and the instrument technologies that are required for a mission of 14+ days to polar regions. And the most important scientific objectives is actually looking at volatiles. And there's a strong emphasis on water there. But we're also looking at the surface radiation environment, which is also of interest to our group. We do have 3 primary instruments. One of them is a drill and mass spectrometer. Then we have a laser-induced breakdown spectrometer, and then we have this what we call the Lunar Cosmic Ray Neutron Spectrometer. Just very briefly, I don't really have time to go into detail here. So basically with this rover, we're also looking at what basically everyone else is looking at. So basically landing, do a site contamination analysis, and then look into sunlit and shadowed regions, going into PSR, looking at the vicinity of large PSR, if there's any spillage of volatiles. And we have identified 6 regions of interest in a very preliminary landing site analysis, basically looking at closeness to PSR, hydrogen abundance, and things like that. And I'm just showing here on the right-hand side, you can see a example traverse that is close to Shackleton crater, actually. So obviously this is work in progress, and since we're only a tech demo right now, further studies are definitely required here. So coming to what our group is doing within that project, we call it the LCNS, so the Lunar Cosmic Ray Neutron Spectrometer, which is basically made up of 2 main particle detectors. One is a charged particle telescope, and that is basically used to characterize the radiation environment on the lunar surface, with a very precise determination of the angular profile as well. Also looking at albedo radiation at very low energies. And then we have a neutron spectrometer that should be sensitive to the aforementioned changes of the epithermal neutron flux. And all of that is complemented by a couple of dosimeters. And obviously, there are other instruments out there like LND, Mini-NS, and so on that do similar things. But we think that the couple of aspects that we're looking at are quite different from what others do here. So just a couple of words about the instrument design. The Charged Particle Telescope is really a very simple setup made out of silicon pixel detectors for tracking of charged particles. So those are the Timex-3 detectors that NASA has been using for quite a lot of missions now. And then in between this very simple tracking telescope, we have a calorimeter made from plastic scintillators and metal absorbers. And then we have a couple additional silicon detectors for the low energy albedo measurement. And then the neutron spectrometer is made from glass scintillators, but we do have active moderators made from plastic scintillators that allow us to do an energy measurement actually in the end. And then obviously we need a veto detector to suppress the charged particle background. To give you a feeling what we're talking about, so we're aiming right now at a mass of less than 4 kilograms, size of below 3 unit CubeSat size, and then less than 15 watts max power. Those are obviously preliminary right now, but this is what we're aiming at. And you can just see here on the right-hand side an engineering model of the Charged Particle Telescope that we recently tested. So basically, the focus of this talk really is on the neutron spectrometer, because that is what gives us our water and hydrogen signature. And then the Charged Particle Telescope is basically for context and background plus a general radiation measurement on the lunar surface. So looking at the performance, most of that is based on simulations with GN4 right now, because we have just begun testing. And what we did, we used the flat energy distributions from 10 MeV over N to 3 GeV over N to optimize a very simple cut algorithm that we have. So basically, we're looking at algorithms that allow us to do on-instrument analysis of the data with very constrained computational resources. So we used a very flat spectrum to arrive at the cuts that you see on the right-hand side here. So here you can see the spectra for different particle IDs, so different ions that we shoot onto the detector. And you can see that we can clearly separate them here for particles that have low energy, so actually stop in the detector. We use this measure of the total energy deposited times energy deposited in one particle layer. And then if we measure the total energy, so particles going through, basically we just use the total. And you can see that we can nicely separate them. So based on these very simple cuts that we have, we're looking at, and this is what we're showing here, the classification of particles. And as you can see here in this kind of matrix, basically we plot what we actually shot onto the detector in the simulation versus what our analysis algorithm predicted. We can see that for stopping particles, we can really achieve very nice values above 80% and way above 90% for lighter ions, and then for through-going particles, it's a bit worse. So we recently did tests with that at the Paul Scherrer Institute and are doing data analysis right now of that. And then as to the performance of the neutron detector, we also did GN4 simulations here, again with a very flat energy distribution between 0.1 eV and 8 MeV. So this is thermal to epithermal neutrons. And we basically defined 3 primary sensitivity ranges here that are roughly modeled after what Feldman et al. Published in their paper. So we just changed a couple of values here slightly. And what we get is what you can see on the right-hand side here. So basically, again, we do this kind of matrix plot where we have the actual energy of the neutron and then drawn against the neutron energy that we reconstructed. And you can see that in terms of classification efficiency, we achieve really, really good values here, close to 100% mostly. And then for the absolute efficiency, numbers are a bit worse because some neutrons get scattered out, some don't interact at all. But overall, we get less than 6% rejection for fastened epithermal neutrons and 100% rejection of the background. So basically, the intermediate goal is to really just do this kind of classification in these 3 sensitivity ranges But the final goal for our flight instrument would be to do a full energy measurement, so spectroscopy measurement. So to conclude, we're currently testing engineering models of the LCNS. Like I said, analysis of the charged particle test data is already underway. We're looking at an integrated test campaign with the Lithiumyx rover, with just a mock instrument, obviously, in September, October this year, and are close to GRL56 now, once we have completed these tests. The funding, unfortunately, will run out in end of this year. So we're looking for potential flight opportunities if EU-funded follow-on funding should not arise. So if you're interested by what I just presented and want to know more details and are interested in cooperating with us, please reach out. You can find my email address here or find me in GatherTown. Thank you.